Hamza Fawzi will talk about what and its universal limits on adversarial robustness. Please go ahead.
Thank you, Thomas. Yes, so this talk is is a continuation of Hussein's talk, and it's actually joint work with him. So the goal of this work is really the following question. So okay, this doesn't work. So Hussein has explained at length that state-of-the-art classifiers are vulnerable to very small adversarial perturbations, and he told us that there's actually we don't have very good ways of solving this problem. So the question that really originated this work is the following: is it actually possible at all to construct classifiers that are robust to adversarial perturbations? I mean, maybe this is not at all possible. Maybe this is due to some phenomena in high dimensions. I mean, our images live in some very high dimensional space. There are some phenomena that we do not understand in high dimensional space that make all this, I mean, the existence of robust of adversarial perturbations that are, I mean, that these phenomena are the root cause of the existence of such perturbations. So the goal is really to derive universal limits or upper bounds on the maximal achievable robustness to perturbations. So Hussein talked to us about, so for any classifier we can associate a certain quantity that will tell us how robust this classifier is. Okay, so high values, okay, means that the classifier is robust, and low values mean the classifier is not robust. And so what we want to do is to derive upper bounds on any classifier. Okay, so we want to show that there is it's not possible to find a classifier that achieves robustness higher than something. Okay, so and our goal is to find something that is true for any classifier. Okay, this is really the goal set in this that I want to make clear. So let me just point out to just maybe one prior work related to this, but then I will explain how it departs from it. So this is exactly the quantity that I told you about. So this is the robustness of a certain classifier f. So what is this quantity? This is exactly, so for any image you can compute, you can think about the smallest perturbation that you need to do to this point x in order to cross the decision boundary, in order to classify it incorrectly. So you can do this for all image, for any image, and then you can take the expectation of this number over all images. Okay, for some distribution. This gives you a certain number. This number is called the robustness of the classifier, rho adv. Okay. And again, what I said is that we want to find upper bounds on this quantity. So this is prior work of Hussein and some co-authors, where they show upper bounds on the robustness, assuming, I mean, with some assumptions on the classifier. For in this case, the classifier is linear. So they prove upper bounds based on the risk of the classifier and some other quantities that I will not explain here. This is not the point. But the point here is that this is an upper bound on the robustness. I mean, assuming some structure on the classifier, but without assuming anything about the data distribution. So I said that I'm taking an expectation here to define rho adv. In this result, you're not assuming anything about the measure mu with respect to which you're taking the expectation, but you are assuming something about the classifier f. Okay, the goal of this work is a shift in the point of view. Okay, so I don't want to make any assumption on the classifier. I want my result to be true for any classifier, but I'm willing to do some assumption on my data distribution. Okay, so the expectation with respect to which, I mean, the measure with respect to which I'm taking the expectation. Okay, and this is motivated by, I mean, recent works on generative models that allow you essentially to generate images at random. Okay, so essentially, so this is the data model that I will consider in this talk. So how images are generated at random is going to be as follows. So I have a certain latent space. So you think about a latent space Z. I mean, in this talk, Z will always be a vector in the latent space. Okay, you generate a random Gaussian vector in this latent space with respect to, with a covariance matrix, the identity. And then you take this vector Z and you map it through some complicated function that I call G, okay? And this is your image, okay? So this is this procedure underlines I mean, a lot of the recent works on generative models, GANs, and so on. I mean, if you think about big GANs, so this is a recent a version of GANs that give you very high quality images. Essentially, I mean, exactly in this way, you generate a random vector of say 100 dimensions, and then you map it through some complicated function g, and of course all the work is to find a good function g that allows you to map this random vector to something that looks like, I don't know, a dog or a cat or a car or whatever. Okay? So this is really, so if you want, my data distribution is really the push forward of a Gaussian distribution by this map G. Okay? Is the data distribution clear? Yeah. And I'm not going to assume anything about my classification function f. So f is a function that takes an image, okay, and gives you tells you whether this is +1 or -1, or whether this is a cat or dog or whatever. Okay, so if I were to picture again, so this is a pictorial representation of what we have. So I have my Z space, my latent space. I have a Gaussian distribution here. Okay, I mean, this in practice, this is usually about 100-dimensional space, the latent space, and you map it through some complicated function g. This is typically a much higher dimensional space. This is the space of pixels. Okay, this could be 1,000,000-dimensional. Of course, because you're going from 100-dimensional to 1,000,000-dimensional, you will get something that lies on a certain low-dimensional manifold. So in this case, this is the circle. Okay, and the data points that we have, I mean, okay, pictorial, we have these as points, and the circles, these are the things that can be that you get by essentially mapping these points in the latent space to things in the image space. Okay, so these are this is my data distribution now in the image space, and now I have a function that acts on this space. Okay, that essentially will divide this space into two. If I have two classes, that will be able to tell me whether an image is a cat or a dog. So for example, here we have two classes, green and blue. Okay. So, and of course so the function f acts on the whole space. Okay, not just on the data distribution here. So so this is the picture. I hope it's clear. And now we're going to define our basic characters of this talk. So these robustness measures. I mean, these are things that Hussein already introduced. So if I have a certain point x, so x is my image, okay, I'm going to think first about the unconstrained robustness, okay, and this is the usual definition that I'm looking for the smallest perturbation of x that will take x from the current class to another class. So x is classified here as red. I'm looking for the smallest perturbation that will, take x and move it to the blue region. Okay. So there's going to be another important character in this talk, which is the in-distribution robustness. Okay, and here we have the constraint that I have to move to an image that is in my data distribution. Okay, so I have to move to an image that is on my circle. Okay, because my circle is really the image of G. Is the image of G exactly? Okay, so it's in my data distribution. Okay, so there's a difference between R unconstrained and R in distribution. And of course, the unconstrained robustness is always smaller than or equal than the in-distribution robustness, okay, because I have more freedom to look for a perturbation when I have with my unconstrained robustness. Okay, so mathematically, we have the following thing. So, okay, so let me actually start first with the unconstrained one. This is simpler. So the unconstrained one, okay, I'm looking for the smallest norm of a perturbation such that so my image that I have is g of z. Okay, so let's see. So this image x that I have is the image of some g of z here. Okay, so x is g of z, and so I look for an R of minimal norm such that f of g of z plus R is different from f of g of z. Okay, this is the usual definition. So now in the in-distribution robustness, what we do is that we move this R, we think about the R vector now not as a vector in the image space, but a vector in the latent space. Okay, so now my R, if I think about the first equation here, I look for a R in the latent space of minimal norm, so this is again a norm in the latent space, okay, such that f of g of z is different than f of g of z plus R. Okay, so my R enters into the G. This is a different, this is the in-distribution robustness, and in fact in the in-distribution robustness there are two notions that you can do. whether you measure the norm in the Z space or you measure the norm in the X space. Okay, this is the subtlety that I want to make sure it's clear in this talk. Okay, so I either think about a perturbation in the latent space or in the image space. So in the image space, that will be the unconstrained robustness. If I think about a perturbation in the latent space, I can measure the norm, either the norm of g of z plus r minus g of z, which is the norm of the perturbation in the image space, or I can measure the norm in the latent space. Okay? Any questions about this one?
It wouldn't give you the same result as probably the perturbation in the latent space that gives you minimal.
Yes, these are all different quantities. These are all.
But there is a third thing, right? So you
Yes.
have a perturbation in the latent space that gives you minimal distance in the.
Yeah, isn't this
Okay,
is the one?
it's that one then.
This is the one. Yeah.
Right.
Okay.
Oh,
So
yeah.
I think about the perturbation in the Z space,
Yeah.
but I measure its norm in the image space. Okay. Okay. So I can actually jump into our main result right away. So what we show is, again, as I said, what we want to show is to show limits on the robustness of any classifier to perturbations. Okay, so this is the result that we prove. So we prove it first for the in-distribution robustness. Okay, so this RZ. And the statement is as follows. So let me try to make this result. So there are many equations here. I want to try to make it just simple to understand here, to how to digest it. So let's assume that you allow for, the maximal amount of perturbation that you allow, let's say, is 0.1 or so. Okay, so meaning that a perturbation of magnitude larger than 0.1 will be say visible to the eye. So 0.1 is the maximum I can allow. So what this result tells you, so you put epsilon is equal to 0.1, you will get a certain number here. It tells you that there is at least that many images in your data distribution that have a perturbation smaller than 0.1. Okay. In other words, that there is no classifier that has the opposite of this. Okay. So that any classifier must have at least this many number of images with a perturbation that is 0.1. Okay, so again, it's in the same spirit that I said. So we want to find upper bounds on the robustness of classifiers. Okay, and this is true for any classifier. We are not assuming anything. It could come from an extremely complicated deep neural network. It could be whatever you want. Okay, but again, we have done this crucial assumption of the data distribution is coming from this push forward of a Gaussian measure, and the probability here, of course, is taken with respect to this measure. Okay. Yes. So you may ask me what this epsilon. So I said 0.1. What should I actually compare this epsilon to? Okay. So you should really compare this epsilon. So again, this because I'm looking here at RZ, and RZ lives in the latent space. So I'm measuring the norm in the latent space. So I should really compare this RZ to the norm of a typical vector from a Gaussian distribution in d dimensions, and we know that the norm of a typical Gaussian vector is roughly root d. Okay, so this is really the baseline that you should compare to, the RZ. And then another kind of so I haven't explained this, but this is also true for any. The classifier can go to any number of classes, and so. What you have here from the second equation is you see that as this is essentially an increasing function of k. Okay, so you have an increasing probability of fooling with the number of classes, and this is something that confirms experiments. Okay, so this is something that we see in experiments, and this result confirms it via theory. Okay. So again, so this is a kind of an upper bound again on the robustness of any possible classifier. So let me tell you how where this result is coming from. So this is coming from a kind of a fundamental result in in probability to something called the Gaussian isoparametric inequality, which is something very related to robustness, and so it's very natural that this is the tool that you need to prove this. So think about the following question. So I live in Gaussian space, so I have RD, which I endow with the Gaussian measure. Okay, and I think about a measurable set A, so it can be anything. And I think about a widening of this set. Okay, so I think about all possible points that are within eta distance from A. Okay, this defines a certain bigger set, which I call A little eta. And what I want to understand is how, what is the measure of the set A eta? What is the volume of the set A eta? Okay, I mean, by widening this set, how large does the volume of A go from, let's say if I start from 1/2, if the measure of A is 1/2, how big is the measure of A eta? So this is actually a very natural question, extremely old question in mathematics, the isoparametric inequality. I mean, before it has been considered in the Gaussian case, it has been considered just in the usual, so in R2, in fact, just with the usual volume measure, where you have a certain, let's say if I have any shape in R2, I don't know, something like this, and you can consider again the widening, okay? And you want to understand, so this is A eta, and this is A, so it's exactly the same thing, but now what I do is that I measure the area of A eta instead of the Gaussian volume here of A. And so the isoparametric inequality essentially gives you a bound on the volume of A eta in terms of A. Okay. So you can see, I mean, at least in the case of 2 dimensions, that the volume for eta very small, okay, that the rate at which the volume of A will change. So if you want the derivative of the volume of this with respect to eta at 0, will essentially be related to the surface area of A. So how big this is. Okay, so okay, so if the surface area is very big, okay, the volume of A eta will increase very quickly, but if it is small, it will not increase as quickly. Okay, so essentially what you have is so in the Gaussian case, so let me now state the result. So the Gaussian isoparametric inequality tells you that if the measure of A is 1/2, okay, then the measure of A sub eta is at least 1 minus 1/2 times exponential minus eta squared over 2. Okay. So I mean, in fact, the Gaussian isoparametric inequality is much more precise than this. Okay, so it tells you really that if you're looking at a set of, so you fix the volume of a set, so the Gaussian volume of a set say to be 1/2, and you want to understand what is the set with smallest surface area, with smallest Gaussian surface area, then it's a half space. Okay, this is really what the isoparametric inequality is telling you. And then we know exactly what if you widen a half space, we know exactly what the volume of A eta is, and this is just an estimate of this. Okay. Similarly, we know in the Lebesgue measure case, so in the case of say R2 or Rn, but with the volume measure, we know that if you fix the volume and you look for the set of smallest surface area, we know that this is a sphere. Okay, and this is called the isoparametric inequality for the Lebesgue measure. And again, I said this is a very old question. I mean, it goes back, if you Google say isoparametric inequality, it usually goes back to the Queen Dido of Carthage, who wanted to build a certain city in Carthage, and so she wanted to build a wall to maximize the area. Okay, and so the question was to find the shape with maximal area with a certain perimeter. And so she solved the problem, and this is actually just a circle. So this is a very old question in mathematics.
I'm surprised that it does not depend on D.
Yes, yeah, this is a very specific feature of the Gaussian case. Yes, yeah, that's a very good point. Yeah, exactly. Yeah. So, okay, so how do we actually apply this result in our case? Let me now briefly tell you. So. So essentially, let's just think of the simplest case. So let's say I have two classes. So this is my set. This is the set classified. So this these are images. Let's say images classified as let's say +1. Okay. So if I think of the widening, the eta widening of this set, so what I get exactly the set of, so this is the set of images, so classified as -1, so the other class, that have an adversarial perturbation of size, of magnitude eta. Okay, because these are exactly the set of images that if you perturb by eta, you will land in a different class, which is the class +1. Okay, so here you're in class -1, so everything else here is class -1, but these guys, if you perturb by eta, you will land in class +1. So this is one part of the so essentially by quantifying the measure of this set here, we can get we know how many so how many images have a certain adversarial perturbation of size eta, and then by using this bound, essentially we immediately get this. And then okay, so this is just for 2 classes. You can generalize this for many classes, and okay, but it's yeah. So so any questions about this result? Is it clear? So essentially, the Gaussian isoperimetric inequality is kind of the right tool in this case to study the the robustness with respect to any classifier. Is the statement clear? Yes, yeah.
Perturbation is happening in your Z space, or?
Yes. So here the perturbation, that's a good point. Yeah, thanks. So the perturbation is happening in the Z space, and I'm measuring the norm also in the Z space, because I'm measuring the norm of the perturbation, everything with the 2 norm. Okay, so in the Z space, exactly. Yes, that's a good point. I will move to the other one now. So. Okay, so okay, but before moving on, let me just comment a bit on this. So so as I mentioned, that the Gaussian isoperimetric inequality is much more precise than this. In fact, we know that the set that minimizes the surface area is exactly a half space. Okay, so meaning that the decision boundary here is a linear function. Okay, so this is the set that has the smallest widening eta. So this actually suggests that if you want to minimize the robustness, so if you want, if you want to maximize the robustness, if you want to minimize this R, then what you want really is to have this region. You want this to be a half space. So what this means is that you want that in your latent space, you want the classifier to be really something linear. Okay, but this is really in the latent space, not in the image space. Okay, so it doesn't say that the classifier has to be linear. It means it has to be linear in the latent space. And okay, and so yeah, so the example that you see here is an example of a set for which the bound is kind of is not tight. So this is a set, if you want, with a surface area that is very big. Okay, so the surface area of this set is much bigger than the half space, and so when you widen, say C1, you get something that is much bigger than what you get with the half space. Okay, so this set is much worse, if you want, from a robustness point of view in the latent space.
Excuse me.
Yes. Sir.
Result apply if you're in a D+1 space and on the surface of a unit sphere in that
yes, so
one space.
The isoperimetric inequality on the sphere and on the Gaussian space are very related. Yes. Well, this is good. So in the sphere, what plays the role of the half space is a spherical cap in the sphere. So this is that. Okay, so let's now. Okay, no. Before I change to I think about the other notions of robustness that I mentioned. Let me just mention this fact. So there's something that has been observed while in experiments, which is this notion of transferability of perturbations. That if you have 2 classifiers of small risk, okay, so then a perturbation that you find for the first classifier will often work well for the second classifier. Okay, so Okay, so this is this result essentially just supports this observation by theory essentially. Okay, so it shows that if I take two classifiers f and h, okay, such that when the probability that they're different is less than delta, which in particular happens if f and h have a small risk, okay, then the probability of finding a common classifier for both, so that there exists a certain classifier, a certain perturbation v that is common to both f and h is bigger than something. Okay, so this is something again that supports what we've seen in experiments. This notion of transferability of perturbations. Yes. So. Yeah, so let's now see what are the ingredients that we need in order. So this is all for the to get bounds on Rz, okay. But really, what I would like to bound is probably Rx, or actually even better would be R unconstrained. So let's see what we need in order to do this. So the simplest way to translate from one to the other is to assume some kind of smoothness on G. Okay, so we assume that G doesn't really distort very much the L2 norm. So this means that the norm of G of Z minus G of Z prime is less than some omega of norm of Z minus Z prime, where omega is some modulus of continuity of G. Okay, so using this assumption, we can transfer anything that we have about the L2 norm in the Z space to whatever norm that we have on the image space, okay, using this G. So for example, let me now give you this is the same, essentially the same result I showed you before, but now with Rx. So this is an expectation. So this is the expectation version of what we have before. So this is a probability result. Now this is an expectation result. So it essentially is a translation of what we have before, but where we now use the modulus of continuity, which here we have to assume it's a concave function. Okay. So it gives you exactly a bound. So again, this is, if you want, this is the rho adv that I had in the first slide. This quantity that I associate to a classifier, which quantifies robustness, and I have an upper bound on this, and this is true for any classifier f. Okay. Okay, and so you can also make this this thing robust. I mean, if your data distribution is not exactly the push forward of a Gaussian distribution, but if it's just if it's close enough to it with respect to, say, some Wasserstein sense, then you can make this bound robust to it. Okay. So okay, so now, so this is what's for Rx. Now a question is, can we actually get a better bound on this notion of unconstrained robustness, which is really what we're after? And the answer is no. I mean, it is no, assuming that what you want to get is a bound on all possible classifiers. Okay, and so you can actually prove, and it's not very difficult to prove. It's essentially just a triangle inequality with a careful construction. That if you give me any classification function f, okay, I can construct another classifier f tilde, okay, such that its unconstrained robustness of this new classifier is at least the Rx measure of robustness of the other classifier. Okay. So of course we always have the other inequality that the unconstrained robustness is smaller, and so this shows the other way. Okay, so it shows that really we cannot hope to improve much on so yes, that the unconstrained robustness and the Rx notion of robustness are really related very closely. So okay, so let me now conclude with some experiments. So these are images generated from a certain. This is a generative model that generates things in. So these are digits in doors and so on. These are okay. So let's. So this is a table that shows us the results. So we compare essentially our bounds to what you can get with methods that construct perturbations. So if I measure things in the Z space, our bounds are pretty accurate. So for example, this shows that with these architectures, what you can find is perturbations of this magnitude, and the bound that we get is this. So telling us that you cannot find classifiers with robustness better than this one. Okay, so this if you measure things in the Z space, but if you measure things, I mean, if you measure the unconstrained robustness, okay, because we have to, we have this modulus of continuity thing that that introduces some conservatism. We get bounds that are kind of an order of magnitude off from what we get using experiments. Okay. Okay. Yeah. So yeah, so this was for one data set, the SVHN data set. This for another data set, C4, and we explore. I mean, we see roughly the same phenomenon, that it's pretty accurate on the measuring the robustness in the Z space, but not so accurate on the measure in terms of unconstrained robustness. Okay, so again, because we're using this smoothness of G that is, we're losing some here in the inequality. So okay, so to conclude, so we proved that no classifier can be robust to adversarial perturbations when the latent space is sufficiently large and the generative model is sufficiently smooth. Okay. Okay, so this is applicable to any classifier, including the human visual system. So maybe one thing that I should mention, I mean, one I think interesting future work is to improve this. I mean, so here we're using just the smoothness of G to transfer the bounds on the Z space to the bounds on the X space, and as I mentioned, we're losing here a little bit. So one interesting, I think, avenue of research is to try to find a better way of doing this, to find bounds directly in the X space, and to also understand. So here we're using an isoperimetric inequality that is true for all, that works, of course, for all measurable sets A. Something interesting that in order to get results that are closer to what we get with deep neural networks is to understand the effect of widenings on the sets defined by deep neural networks. So on these sets that are generated by the deep neural networks. So yes, so I will conclude here. Thank you. Thanks.
Questions?
Yes, Sergio.
I wanted to clarify something. So, in your experiments, when you compute the theoretical bounds,
Yes.
You're estimating the smoothness of the
Yes.
generator, and so that's where you think you're losing.
Yes, exactly. Yeah, exactly. Yeah.
And
Yeah,
how are you doing that for this type of neural network?
Yes, so I think we're sampling some data points. It's not, okay, of course, we cannot exactly get the modulus of continuity or the Lipschitz constant, whatever it is, but we're just sampling points, and we're estimating from samples, yeah, the Lipschitz constant, yeah. So,
More questions?
How restrictive is the concavity assumption in practice?
no, it's not restrictive, yeah. It's, I mean, so really this is just to kind of, yeah, I mean, Lipschitz is fine. I mean, we can, so just a linear thing is usually. So, I mean, of course, the bounds that you get using this are going to be more conservative, of course. I mean, this thing of going from the Z space to the X space via this modulus of continuity we lose here. Yes, so I mean the concavity itself is not the main issue. Yeah. So.
What is the main issue then if Fermi champion?
What is the main issue?
Yeah.
So the main issue is to try to understand the perturbations in the X space directly rather than in the Z space, and then transferring it through via some modulus of continuity.
So this is why you need the Gaussian assumption in the first place to.
Yes. Yeah. Yes. Yeah.
Time for another question. Yes.
So my question is that, maybe the technical question as to, you have your Gaussian generative model.
Yes.
How do you get the G is the inverse problem, or for your data generation, I'm saying, for your experimentation?
Yes, no, so the experiment, we're taking some existing GANs, we're not learning new Gs. So there are many, you can find many Gs out there in the...
That will give a cat from the Gaussian distribution.
Yes, yeah. This is exactly this big GANs and so on. I mean, this is a very big thing. So, yeah, big GANs. Where's it? Yeah. So, anything else?
No more questions, then let's thank our speaker again.